Hello. I'd like to talk just a few words about uniform heating of multistructural biological objects by means of electric and magnetic fields phased emitters. The main problem in applying vitrification techniques to bulky tissues and organs are related to the difficulty in achieving sufficiently rapid and uniform warming rates that are necessary to avoid devitrification. Non-uniformity of temperature increases the risk of mechanical stresses and factors development of the glass during rapid warming. Heat-bound conduction become increasingly indicates as the size of the tissue increases, and once the tissue exceeds a few millimeters in thickness, can lead to excessively high temperatures on the periphery when the core remains vitrified. Such large temperatures gradients also lead to mechanical stresses, factory and tissue damage. Electromagnetic absorption, dielectric heating, as an alternative method for warming of bulky tissues, had been the subject of study for over 25 years. Early studies on wall tissues using conventional microwave ovens operating at frequencies at 2.4 gigahertz, but it were not successful. It was later established that a low frequency would give a greater penetration depth and better uniformity of heating. And the optimum frequencies range for dielectric heating of the it's from 300 to 1 megahertz to 1 gigahertz. Uniformity of warming in a dielectric field is heavily dependent on the dielectric properties of the aqueous phase, and in particular its cryoprotectant component. Still, the best results was a purpose-built power source and resonant applicator operating at 434 megahertz was produced at relatively uniform heating across 36 millimeters gelatin spheres containing various concentrations of dimethyl sulfoxide, with the final maximum temperature difference not exceeding 9 degrees by Celsius. We describe an approach to achieving uniform heating of bulky multistructural biological objects by coherent electromagnetic radiation with zero field intensity region, guided by the data that we take by MRI thermometry. Our method consists in the use of high frequency heating in order to uniformly heat of heterogeneous tissues. For that, we suggest to use a proposed focusing of coherent electromagnetic radiation to obtain regions with zero electric and magnetic field component. Creating a point of zero field stretch will be obtained by placing a minimum of 4 emitters in corners of tetrahedron in 3 dimensions. The power of emission and phase of emitters is defined on the basis that provide 0 point within. For 2 sources of field on this diagram, on the one line, we see that if we use 2 sources with field shifted on 180 degrees, the total field strength in point A was 0. If we need to work in 3 dimensions, we use 4 sources of the field. And by changing phase and power, we may in any moment have 0 point in any point of this volume. We change the emission power of the emitter, power and phase of the emitter, and point A moves on the x-axis between the emitters for 2 sources. We solve the system of linear equations in which the initial data as size of the object, heat capacity of each virtual object point, I say point later, absorptive capacity of each point, and the initial value of the temperature in each point that we take from MRI thermometry. The solution is represented by a matrix with the following set of elements. For each coordinates, we calculate energy and phase and time of heating for each for working. The matrix will that provided on the picture determines the work of the magnetic and electrical fields of emitters. The application of electric fields is more complicated due to the nature of its distribution. There is a reason why we suggest to use two types of fields. Objects at low temperatures are more effectively heated by the capacitive method. A function of magnetic field depends from an electrical conductivity for the heated material. And at the same time, objects with higher temperatures are more effectively heated by magnetic field. Application of this method required a solving of the matrix for list for emitters. More sources of emission, such as inductors of magnetic field and the capacitors for electrical, is associated with a difference of solving the matrix. So it would be helpful to state the emitters are located on the surface of the conceptual sphere in order of reducing the dimensionality of system. More precisely, the set of nested spheres. So we could avoid excessive tension on the borders of the field-heated object. Basically, we calculate phases, capacities, and time of concentrate the point A, that we zero field point, in each point of heated object. It could be done by using a matrix obtained a three-dimensional MRI thermometer. Raw data is getting through information processing of variations, and result we have three-dimensional matrix of specific heads. Most basic application of the method could be represented as move or virtual point on known head with high speed in volume of the heated sample. It's like a deflected beam as television picture tube. More accurate linkers could be represented as accelerated in hundreds of thousands times repetitive work of three-dimensional printer. We could use more effective parts for movement depending on the structure of the heated object, but they have to be discovered first. Mathematical tools are extremely difficult in any case. We have to use either supercomputers or create hardware implementations for the math model using large numbers of FPGAs in order to monitor the temperature of the object in real time. We hope that this technique will allow to reach previously unattainable speeds of rewarming from cryogenic to near zero temperatures, including non-vascular areas and cavities. That was allow achievement of rapid and uniform warming rates that are necessary to avoid vitrification even with reduced cryoprotectant concentrations, thus eliminating the main problem in applying vitrified textures to bulky tissues and organs. Briefly, that's all. If you have any questions, I waited.
So, any questions? Aubrey.
You may have answered this already. I'm sorry if I missed it. But how densely do you need your coordinates to be? I mean, how many dots per centimeter or whatever do you think you would need?
It's the definition of this is what kind of object we try to hit, and resolution of MRI thermometry and MRI first. First, we do an MRI without MRI thermometry to determine the structure of objects that we need to hit. Then, first calculation of matrix. Then we do an MRI thermometry for each point that we plan to hit. On first step, we provide plan of heating, calculate this plan. Then we do MRI thermometry. Then we put object into our volume that have 4 emitters, try to heat it up to maximum 10 degrees. Then we control about MRI thermometry, correct metrics, and step by step we going up to 0 temperature. But maximum resolution is resolution of MRI thermometers that we have.
And what is that? What is that resolution?
Now, actually, we have no MRI thermometer in our lab. We have only mathematics and heaters. But now we ready to correct our technology for using under MRI thermometer control. Thank you.